Section 6.2. A quick review of the properties. First of all, when we have the same base, remember we add the exponents, so this would be a to the m plus n. Distribute the m, a to the m, b to the m. Subtract the exponents, a to the m minus n. Distribute the exponent, so it would be a to the mn. Negative exponent, we put it on the bottom of a fraction. So it would be 1 over a to the positive m. And then here again, you distribute the m onto both things in the parentheses. A to the m over b to the m. We're going to use those properties to simplify when we have rational exponents. Same base, so the base is going to stay 5. Now I'm going to take 1/2 plus 1/4, and that is going to be 3/4. That is simplified. Moving down to the next one. The first thing I would do with this problem is distribute the 2 to both of those. And remember, we need to multiply those exponents when we distribute them. So this is going to be 8 to the first, because 2 times 1/2 is 1, times 5 to the 2/3. And since these bases are different, that's all we can do for that problem. Next one. There's a couple things we could do. We could distribute this 2 right now the way it is. Another really super cool thing, when you have the same exponent in a fraction, you can actually divide these two numbers. So that's what I'm going to do. 12 divided by 4 is 3, but then I still have to put that to the 1/3 because that was our common exponent. And then I still need to take that to the second. Now that's just a matter of multiplying those exponents. So it's going to end up being 3 to the 2/3. Next one. Again, you could do a couple different things. You could put this all on the bottom of a fraction first, or you could distribute this -1/4. That's what I'm going to start with. So I'm going to end up with 3 to the -1 times 5 to the -1. And then we have to put both of those on the bottom since they're both negative exponents. So it'll be 1 over 3 to the first, which is really just 3, times 5 to the first, which is really just 5. And then I can multiply those out. Kind of think the same thing, since those are the same exponents, we can multiply those together. So you've got 1 over 15. Plus we do know that 3 times 5 is 15. Next, since the bases are the same, remember this is 8 to the first on the top. So if I subtract those exponents, it's going to be 8 to the 3/4. And that would be the answer for that one. Next one, we're going to distribute the 3/2. So it's going to be 3 to the 3/4, 1/2 times 3/2, times 5 to the first. 2/3 times 3/2 is 1. And again, since these bases are totally different, that's as far as we can go. Let's talk about perfect cubes, perfect fourths, and perfect fifths. Basically what this means, 1 to the third, since these are cubes, 1 to the third is 1, 2 to the third is 8, 3 to the third is 27, 4 to the third is 64, 5 to the third is 125, 6 to the third is 216, and so on. And then we have the fourths and the fifths. And we're going to use those to solve the next problems, to simplify. If I want to simplify these two radicals, since they have the same index on the radical, I can go ahead and multiply the insides. That's going to end up being the cubed root of 64. Now if you look, 64 is a perfect cube. And also, if you notice it's the fourth number over from the list I made, that means that 64 is 4, since it's the fourth one over, it's 4 to the third. That means that the cubed root of 64 is 4. because 4 times 4 times 4 is 64. And that would be our simplified answer. Next one, again, since these both have the same index on the radicals, I can put these together by going ahead and dividing. 40 divided by 5 would give us 8, and then the cubed root of 8 is 2. You can always go back up here and look at this list. Since that 8 is in the second spot, then the cubed root of 8 is 2. Now we've got fourth roots. Again, since they're both the fourth root, I can go ahead and do the division. 162 divided by 2 is 81. Now we need to go and look at the perfect fourths. 81 happens to be a perfect fourth. And since it's the third number in, that means the fourth root of 81 is 3. Because 3 to the fourth is 81. Now the next one we have to do a little simplifying by breaking this down. If you look at your perfect cubes, okay, we need to go to at least 54, so it's going to be 54 or below. 64 is too high, so I'm going to start with 27. I'm going to ask myself, does 27 go into 54? It does 2 times. So I'm going to break this down. I'm going to break 54 down into 27 times 2. Okay, let's write this out as 2 separate radicals. This really is the cubed root of 27 times the cubed root of 2. And you don't have to do this every time, but just so that you understand what I'm doing here, I'm starting with the cubed root of 27. That's 3. And I know that because it's the third one in on the perfect cubes that I listed out. The cubed root of 2 cannot be simplified because there's no perfect cubes that go into 2. So I'm just going to carry that over. So I've got the cubed root of 2 left. So we've got the cubed root of 27 was 3 and the cubed root of 2. So this would be my simplified answer. 3 times the cubed root of 2. Next one. Now if you remember, we learned before that we need to rationalize the denominator. The first thing I'm going to do is I'm going to start by writing this out as 2 fourth roots. Okay, so I can rewrite this as the fourth root of 2 over the fourth root of 3. Now remember, when we rationalize the denominator, we do not want any radicals in the denominator. But here's where roots above the square root, so once you get to cubed root, fourth root, fifth root, and so on, you have to do this a little bit differently. Think of it this way. I need 4 of something. Right now, I only have 1 3 underneath the fourth root. I need 4 of them. So what I need to do is I need to multiply by the fourth root of 3 cubed. Okay? I have 1 3, I have 3 more 3's, so I'm going to have 4 3's altogether. We always need as many as there are the index. So I'm going to multiply the top by that also to keep this still the same fraction. Now I'm going to put these together, so I've got the fourth root of, this is going to be 2 times 27, that's 54. Okay, 2 times 27, 54. Now on the bottom, what I really have at this point, 3 times 3 cubed is 3 to the fourth. And that's what I wanted. And the reason for that is when you have the fourth root of something to the fourth, that just gives you the number that's left inside, the base number, which happens to be 3. Fourth root of 3 to the fourth is 3. Then my last question would be, fourth root of 54, are any of these numbers, because they're perfect fourths, do any of these numbers below 54, like 16 and 1, do they go into 54? No. So that is simplified as far as it can go. So that would be our answer. Again, this one gets a little tricky. Now, again, I'm going to write this as the fifth root of 3 over the fifth root of 4. Now this is where this gets a little bit difficult to simplify because sometimes it's hard to see. Now, I could add, since I have 1 4 here, I could multiply this by the fifth root of 4 to the 4th because I need 4 more 4s. But something to start paying attention to or noticing is whether this number inside is a perfect square, perfect third, perfect fourth. I'm going to rewrite 4 as 2 squared. That's going to make these numbers a lot smaller and a lot easier to work with. So now let's think. We have 2 2's because we've got 2 squared, so we've got 2 2's. And if I need 5 of something, then I need to multiply this by the fifth root of 2 cubed. So I had 2 2's here, I add another 3, I'm going to end up with 5 2's. Okay, and we do that to the top and the bottom. Now I'm going to put these together, so I'm going to have the fifth root of 3 times 8 is 24 over, and again, if I put these together, that would be the fifth root of 2 to the 5th. So when I simplify this, the fifth root of 2 to the 5th ends up just being 2 because the fifth root and 2 to the 5th cancel each other out. You were left with the base. Fifth root of 24, there's no number besides 1 that is a perfect fifth that goes into 24. So I'm going to leave that as the fifth root of 24. So there's my simplified answer. Fifth root of 1215. If we go to our perfect fifths, are there any numbers below the 1215 that go into 1215 evenly? The 1024 is not going to work, but 243 does. Okay, so I'm going to break this down into the fifth root of 243 times 5. 243 times 5 is 1215. Now if you go back down here, since 243 is a perfect fifth and it's the third one in, that means that the fifth root of 243 is 3. So now that's outside the root because the fifth root of 243 is 3. But then I'm still left with the fifth root of 5. And that comes from this 5 that was left over inside the radical. Now we're going to put a couple radicals together. First of all, you'll notice that we have 2 integers outside of these radicals. You can go ahead and multiply those together. 2 times 6 is 12. Now we're going to put the stuff inside the radicals together. 27 times 9 is 243. Okay, but now that's a perfect fourth that we're looking for. So if we go down here, I know that 81 does. So I'm going to break this down into 81 times 3. Okay, so I still have 12. The fourth root of 81 is 3, so I'm going to put times 3 out here. And then the fourth root of 3, this guy inside here, is left over. So I'm just going to write that down, fourth root of 3. So my final product, 12 times 3 is 36, and the fourth root of 3 is left over. There's my answer. Again, take the 2 numbers outside, multiply those together, 15. Put the radicals together since they're the same index. 24 times 2 is 48. Look at your perfect fourths. 16 goes into 48. So I'm going to rewrite this as 15 times the fourth root of 16 times 3. 48 is 16 times 3. So I've got 15 times the fourth root of 16 is 2. But then I still have this guy left inside, so I'm going to keep that inside the radical, fourth root of 3. And then to put this together, 15 times 2 is 30, and the fourth root of 3 is left. So there's my simplified answer, and that concludes section 6.2, part A.